Most of us don't think of water heaters very often. After all, they usually just do their thing, and the only time they cross your mind is when they stop doing their thing and you have a very unpleasant morning. But water heaters are among the most energy-intensive appliances in our lives. Though we take it for granted, having hot water on demand is so energy-intensive that a very ordinary water heater can cost upwards of $50 a month to use. But this water heater costs an average family less than $20 a month, and in the summer, using it is arguably free. How on earth could that be? Because this machine heats the water inside the tank by chilling the air surrounding it. This is a heat pump water heater, quite literally the coolest kind of water heater you can buy. Traditionally, to heat water we have had to import heat energy from an external source, either the power grid or some sort of heating fuel like natural gas or propane. This water heater, on the other hand, uses the same technology as your refrigerator, but in reverse. Your fridge works by pulling heat out of its interior and throwing that heat outside, which is why your fridge gets warm as it runs. But this thing gets cold as it runs because it does exactly the opposite. It collects heat from the air around it and bottles it up inside. This may seem like a strange way to heat water, but relocating heat which is already there requires just a fraction of the electricity that releasing new heat with an electric heating element does. As in, as little as 1/4 as much electricity. And this is not just any heat pump water heater. It's a 120-volt model, which simply plugs into a standard household outlet. For those of us in North America, that is a really big deal. Up till now, electric water heaters needed to be hardwired to a dedicated 240-volt circuit. So if you had a gas water heater, switching to an electric one rarely made much sense. You'd first need to run a new circuit for it, which can be quite expensive and sometimes not even possible. And even if you were up for that, the power-hungry nature of traditional electric water heaters makes their operating cost a good deal higher than gas. But these things completely change the equation. As they run, they merely sip a few hundred watts. That's why all they need is a power outlet handy. Best of all, because of the magic of heat pumps, the operating cost of this electric water heater is in fact less than the gas-fired water heater it replaced. Well, slightly. Look, let me get this out of the way. I did not install this expecting it to save money, and if you have a gas water heater, neither should you. The significantly higher upfront cost of a model like this means with today's average prices for gas and electricity, it's going to take like a decade to pay for itself, assuming it ever does. The actual math depends, of course, on your local energy prices, and certain situations like rebates and incentives will accelerate that timeline. And also, who knows what energy prices will do these days, so the math will undoubtedly change in the future. But aside from making electrification easier and kind of cheaper, they offer some really intriguing benefits, especially during the warm months of the year. Of course, though, they do have some downsides, some of which are quite significant and could be a showstopper to some families. I'll explain all of that, of course. In fact, puzzling through and testing the various trade-offs involved with these is precisely why I wanted to get one. You see, I am in the worst possible position to have a heat pump water heater, and many plumbers, including the one I ended up hiring to install it, would call me crazy for wanting one. Why? Well, the fact that they cool the air to make hot water is a little inconvenient for those in cold climates. And I live in Chicagoland, which gets pretty frickin' cold in the winter! Now, if your water heater lives in a basement or some other place you don't spend much time, like a utility room, cold climates aren't necessarily a big deal at all. This will make that space a bit colder, but you're not likely to notice that anywhere else in your home. But I live in a townhome without a basement, so my water heater lives in a cramped utility closet. That meant there was more work to do than just the plumbing. And for the icing on this inconvenient cake, that utility closet is in my living space. So using hot water will make the adjacent room colder. But, you see, because energy is energy, I did a little math which led me to think it probably wouldn't get all that much colder, and spoiler alert, I was right. Yes, long story short, I do not regret this one bit, and can now state with pretty high confidence that anyone suggesting these are inappropriate for cold climates is full of it. I won't say they work for every situation because they don't, and they still have trade-offs which you'll need to consider. But based on my testing, those trade-offs are actually a lot smaller than they seem. So, if you're into this whole electrification business, or are simply intrigued by the idea of a water heater that just sips electricity while it gobbles up heat and provides free cooling in the summer, oh, you better believe we'll get to that, then I think these are very much worth looking into. But they are a little different, so let's go over the things that might make the installation process a tad tricky. Emphasis on might. In many situations, installing one of these is incredibly straightforward. Despite how radically different its fuel source is, in most ways this is a very ordinary water heater. It has standard topside water connections, which will be familiar to any plumbing professional. And well, it's a water heater. But it does need two things most water heaters don't. First, just like an air conditioner, this dehumidifies the air when it's running, and thus it produces condensate, so you'll need a drain nearby or a condensate pump to deal with that. And second, in order for the heat pump to capture energy from the air, it has to ingest warm air and expel chilled exhaust, and thus the water heater needs space to breathe. If your water heater is located in a utility room or basement, it will probably have enough space and there will be nothing to do. The manufacturer of this model states that it needs just 450 cubic feet, or 12.7 cubic meters, of accessible air volume. That's not very much at all. With 8-foot ceilings, we're talking a room that's about 6 by 10 feet. So long as your water heater lives in a room at least that big, and, an important caveat for some of you, that room stays above freezing temperature, you can just install this like any other water heater, figure out your condensate drain, and plug it in. But because my water heater lives in a utility closet, it's going to need some help getting enough air. And this is one of two reasons why I chose this specific model. A.O. Smith has equipped their heat pump water heaters with 8-inch collars on the top for both the air intake and the exhaust. Nobody else does it like that, which is a shame, because those collars allow for a huge variety of simple air supply and discharge solutions using flexible ducting. For instance, if you want to pull air from one room and discharge cold air to another room, like maybe an unfinished part of a basement, it's relatively easy to do that. And given the particularities of my home, I wanted some flexibility to tinker with down the road. You may also notice this water heater is gigantic! That's partly due to the fact that it has a heat pump sitting on top of it, which makes it much taller than usual, but it's also much stouter than usual. And that's to make the tank real big to make up for its slowness. Yes, this is the major catch of a 120-volt plug-in heat pump water heater. They are glacially slow. Now, if you already have a 240-volt electric water heater, then you should know that hybrid heat pump models exist, which have both the heat pump and the same traditional heating elements as usual. As a matter of fact, those have been around for quite a while, and frankly, if you've got an electric water heater, they're kind of a no-brainer, assuming you have an appropriate space for one to live. Their hybrid nature allows them to use their slow heat pumps as much as possible, which can save up to 75% on your water heating costs. But if you use a lot of hot water at once, they can switch to those power-hungry heating elements, which quickly heat the tank back up. This one, though, can't do that. All it's got is the heat pump, and that makes it very slow at recovering from heavy uses of hot water. Now, this likely will not matter to you except when you first install it. But if you do run out of hot water with one of these, it's gonna be a while before you get it back. So every manufacturer recommends upsizing to give you a larger buffer between hot water uses. I had a 50-gallon gas water heater before, and that's why I went with this 66-gallon heat pump water heater. And for those of you with the room, these are also available with 80-gallon tanks. Now, a tape measure proved there would be plenty of room for this behemoth to fit in this closet, and the drain in the floor meant the condensate situation was going to be trivial to solve. But getting it in there wouldn't be so easy, because there was stuff in the way. To actually position it required removing and reattaching the exhaust pipe from my furnace. Also, the drain line for my home's fire sprinkler system needed reconfiguration, as originally it was a straight shot from here to there, which intersected with the larger footprint of this thing. For those of you who keep asking, that's why I have this fire alarm bell. If a sprinkler head pops and water starts flowing through the system, that thing will go off. These challenges, though they did complicate the installation somewhat, would be small potatoes to an experienced plumber. But one thing that isn't normally in a plumber's purview is the ducting part. I knew this could be an issue for getting bids. And it was. So I told the plumber I hired that I just wanted him to do what was necessary to get it positioned and plumbed, and that I would initially just keep the closet doors open until I figured out how I wanted to do the ducting. Luckily, he agreed. After the necessary work was finished, the water heater was filled with cold water, plugged in, and it got to work. And indeed, it took quite a while for this thing to get 66 gallons of cold water up to 120 degrees Fahrenheit. I didn't have truly hot water again until the wee hours of the morning, which is something you should be prepared for if you decide to get one of these. Another thing you should be prepared for is a bit of extra noise. This is particularly pertinent in my case, since this isn't hiding in a basement. Now, I absolutely love the sound of refrigeration, so I am biased. But it's really not that loud. I'd say it's a bit louder than a typical fridge. You can barely hear the fan at all, but the compressor does get a little buzzy as refrigerant pressure builds. With the closet doors shut, though, it's pretty tame, and I cannot hear it anywhere else in my home but this room. Also, it's nowhere near as loud as the furnace next to it. Here's what it sounds like when my air conditioning comes on. Yeah. Oh, and ironically, in my case, the gas water heater that used to be here was genuinely louder, since it had a powered vent blower. But anyway, when I woke up the day after installation, I had both 66 gallons of piping hot water ready to go and a job to do. I got incredibly lucky with this utility closet because there was already a vent above the closet doors directly over the water heater. So I just used an 8-inch to 6-inch reducing collar, some 6-inch flexible duct, and an adapter boot to connect the vent to the water heater's air intake. And now the water heater gets supply air from outside the closet. I have since learned that vent was there for code reasons having to do with gas appliances in an enclosed space. So technically I shouldn't have done that, but A, eventually I intend to get rid of the furnace and replace it with a heat pump, and then there won't be any gas appliances in here. And 2, these folding doors have about a 1-inch gap on all sides, so this closet was never truly enclosed in the first place, and therefore I feel no shame whatsoever in being a wee bit naughty. Oh, and that gap is why I didn't bother doing anything for the exhaust. The water heater is blowing cold air into the closet, but it finds its way out eventually. Because of a quirk of my home's HVAC system, I have played around with things a bit since it was first installed, but it's just been tinkering around the edges, and frankly, this duct was all I needed. Quick maintenance note, these things have an air filter which needs periodic cleaning. It can tell when the filter is starting to get plugged up and puts a message on the display, but checking air filters isn't usually something you have to think about with a water heater, so I figured I'd mention it. Oh, also, for those of you who know what an anode rod is, well, should you need to replace it, that's quite a bit more involved than usual, since you have to take the top shroud apart to get access to it. But most people never ever touch the anode rod, so I don't really think that's a big deal unless you have a history of smelly water, but then you probably already knew what the anode rod is. Anyway, everything else is just normal water heater maintenance. So now, you may be wondering why I went through all this trouble to install a very slow, gigantic, expensive, somewhat noisy, and esoteric water heater. Well, the simple answer is I'm a heat pump enthusiast. I'll never say no to a heat pump. And this is such a cool use of one. During much of the year, the last thing I want is to add heat to my home. In fact, I pay for electricity to run a heat pump, which removes heat from my home. Though we Americans call that air conditioning for reasons which aren't important, but apparently is very confusing to certain Northern European thought leaders and policymakers at the moment. Actually, maybe this thing will help with that. See, if you take a look inside the top, you'll find most of the same parts that you'd find in a small window air conditioner like this. That's because air conditioners, get this, are heat pumps. What we call air conditioners are just one-way heat pumps, which can only provide cooling. To do that, they take heat energy from indoors and move it outside. When you stick this thing through a window or even just a hole in a wall, then this heat exchanger, called the condenser, will sit outside, while this second heat exchanger, called the evaporator, stays inside. And when it switches on its compressor, the refrigeration cycle kicks into gear, and it will pump heat from the indoor evaporator to the outdoor condenser. This lowers the indoor air temperature and produces cooling. But what if, instead of just pumping that heat outside to get rid of it, we did something useful with that heat, like, oh, I don't know, produce hot water for bathing and other domestic purposes? Oh, wait! Yes, that is exactly why this has an air conditioner sitting on top of it and why it makes the room colder. It's doing the exact same thing that an air conditioner does, absorbing heat from the air and moving it somewhere else. The only change is that the somewhere else in question is a great big tank of water. The compressor on top is pressurizing refrigerant into a long stretch of pipe wrapped around the water tank a whole bunch of times. Just like the condenser in this air conditioner, that piping will release the heat absorbed in the evaporator. But since that piping is in physical contact with the water tank and buried under several inches of foam insulation, the water inside absorbs that heat, and over time, it gets hot. So it's a water heater. This may seem like a rather convoluted way to produce hot water, but the thing about heat pumps is they can move more heat energy than they consume in the process of doing so. On average, when this water heater runs, it only draws about 400 watts from the wall. But since those 400 watts are running a heat pump which can yoink about 1,200 watts of heat out of the air, 1,600 watts of total heating power ends up being released into the water from just 400 watts of electricity. That fourfold increase in heating power is how these things are so cheap to run, and why this one can get away with a regular plug. That's amazing enough on its own, but in the summer months, when I'm going to pay for using my air conditioner anyway, using hot water becomes effectively free. Think about this for a moment. With every other water heater out there, taking a shower results in either thousands of watts of electricity getting imported from the power grid, or, as was the case for me, starting a literal fire and burning natural gas. This thing, though, each time hot water is used, starts sucking heat right out of the air. In the summer months, I now get extra cooling and dehumidification as a free side effect of using hot water. It's not literally free cooling, of course. The energy used by the water heater itself was not free. But every kilowatt hour it consumes in the summer to generate hot water happens to do essentially the same work as a kilowatt hour running my air conditioner does. So every dollar I spend on hot water saves a dollar on cooling. Now there are two giant asterisks there. First, and here's a bit of foreshadowing, it doesn't actually produce all that much cooling. In fact, I've been disappointed by how rarely it kicks on, and thus how little it seems to help the humidity situation in my home. Now, I don't use very much hot water, but a typical family of 4 taking daily 20-minute showers and running a load through the dishwasher, will probably only see this thing run for 5 or 6 hours a day in the summer. And my central air conditioner, which is on the small side at only a 2-ton unit, is roughly 5 times as powerful as this thing. So in the best case scenario, this might offset an hour of air conditioning use. That's not nothing, but it's also not that significant. Still free hot water though, if you agree with my accounting. And the second asterisk is that accounting only works if the water heater can actually get the cooling it produces somewhere you need it. If this is puttering away in a basement, then sure, it's making your basement a little cooler and drier, but it's probably not helping upstairs. Again though, that's what's so cool about these models having those collars for ducting. You can run ducts however you'd like, and can potentially switch stuff around from season to season depending on your needs. In my case though, this room is where my HVAC system gets literally all of its supply air. The designers of my home used the switchback staircase, which connects the 3 floors, as a giant air return, and this room is at the bottom of those stairs. So whenever my HVAC system runs, it's actually pulling air from this room and distributing it throughout my home. Thus, this is genuinely helping my air conditioner, which is very cool. And you know what else is cool? I now have an emergency cooling source permanently set up and ready to go. See, I have one of those electric cars which lets you plug stuff into it. And I have now confirmed this water heater will happily run from my car. So if, say, there were a widespread power outage during a heat wave, I can run an extension cord out to the garage, plug the water heater into my car, and fill the bathtub with hot water. Once the water heater starts up to replenish that water, it will produce a similar amount of cooling as a small window unit. That's not a lot of cooling, of course, but during a test where it was 96 degrees Fahrenheit outside, the water heater was able to keep the room it's in below 68 degrees, despite my central air conditioning being completely shut off all day. So I know at least one room of my home can stay nice and cool using backup power from my car and, weirdly, a bathtub. This could also come in handy if, my air conditioner conks out. Doesn't have to be a power outage. But what about the winter months? Generating cold air as a consequence of producing hot water isn't quite so appealing when it's below 0 outside. Well, that's why I installed this thing back in early February. I deliberately did this in the dead of winter because that's when the situation isn't quite so rosy. In fact, people are so put off by the idea of having one of these in the winter that split heat pump water heaters, which use an outdoor unit to gobble heat up from outside air, are becoming a thing. Boop. But for the most part, I've honestly been a little puzzled by those. For one, you don't get the free cooling you do with this, but for two, by my math, the hot water usage of an average family shouldn't drop the indoor air temperature all that much, and thus, split heat pump water heaters feel like a lot of extra work for a potentially marginal and only seasonal benefit. So basically, I wanted to figure out if my math was right or not. And it was. To provide you with an objective measure of the impact installing this would have, I put temperature loggers throughout my home many days before it was installed. And here's what that data looks like in the room in which the water heater lives. Can you tell when on this graph the heat pump water heater was installed? It's pretty difficult, isn't it? It was switched on for the first time right here. And yeah, the room got a bit colder, but this was the first time it had ever run, so it needed to heat the entire tank. During this section, the water heater was running non-stop for over 10 hours. But since the furnace kept kicking on and adding heat in response to the temperature upstairs, the room stayed at pretty typical winter temperatures the whole time. Wait, did I just say it was running for over 10 hours? Uh-huh! I did say these were glacially slow. But before I get into whether or not that will matter to you, it probably won't, I want to note that while I was logging temperature data in plenty of other spots around the house too, none of that data turned out to be interesting in the slightest. Which is irritating because I bought more data loggers so I could log 10 different locations. But for instance, take a look at the temperature upstairs near the thermostat. If I overlay the temperature graph from inside the utility closet, we can see when the water heater was running as a sudden drop in temperature. And if I highlight those regions, you'll discover that it made absolutely no noticeable difference at all to the temperature upstairs.
Okay, well, that needs picking apart. First, this data looks so spiky because I lower the thermostat by a few degrees at night, and even more so when I'm not home. And remember, this logger was next to the thermostat, so we shouldn't expect to see much impact from the water heater since, well, if there is any impact, the thermostat is just going to react and switch the furnace on. So while it looks like the water heater might have caused this drop here, in actuality, this was just before I went to bed, and thus the thermostat set point was lowered. So instead, let's switch to the data logger, which was in my living room right next to the staircase. This spot is the closest you can get to the room the water heater is in without actually being in the same room. And as you can see, whether the water heater was running or not had virtually no bearing on the measured temperature. Now again, because I don't keep my home at a stable temperature all day long, it requires careful analysis to see the true story. But notice that here, when the furnace hadn't been running for quite a while and the temperature in my home was dropping as a result, the water heater switching on didn't accelerate the decline. The slope appears virtually unchanged. And here, when I actually was keeping a steady temperature in the house, the water heater made no detectable impact. Literally the only room in my home the water heater makes noticeably cooler is the room that it's in. And even then, it's a minor effect. Both real-time observation and these logs indicate that in the winter months, the water heater is only making this room between 4 and 6 degrees cooler, and only when it's running.
And now, if you'll indulge me, let me explain how math got me to this answer ahead of time. The reason I'm constantly saying energy is that once you develop an intuition for it, you'll be able to make predictions. Elevating all 66 US gallons of water that this can hold from 55 degrees to 120 degrees is the same thing as elevating 250 kilograms of water by 36 degrees Celsius. Now, a calorie is the amount of energy needed to raise a gram of water by 1 degree Celsius, and so raising the 250,000 grams of water in this tank by 36 degrees Celsius requires 9 million calories. That's gram calories, by the way, not the kilocalories we measure food energy with. And so long as Google keeps this handy calculator handy, we can simply convert that 9 million calorie figure to roughly 36,000 British thermal units, which is the unit we typically use for heating and cooling. So we now know roughly how much heat energy the water heater will have to absorb to heat the entire tank of water in the winter: 36,000 BTUs. In actual fact, it will likely only absorb about 27,000 BTUs, because roughly a quarter of its heating power comes from the electricity it consumes. But we'll go with the bigger number to show just how much of a nothing burger this is. Sure, this may yoink 36,000 BTUs of energy from the air to heat a full tank of water. But my furnace can put out about 55,000 BTUs per hour. So, to heat the entire tank of water requires the same amount of energy that my furnace puts out in just 40 minutes. Now, we've established that my furnace is wildly oversized for my home, but the point remains, these simply do not have that drastic of an impact. Water heating is energy intensive, but space heating is much more so. But how about we compare cooling to cooling? My 2-ton central air conditioner can remove 24,000 BTUs per hour from my home. So running my air conditioner for just 90 minutes will produce the same amount of cooling that this thing will as it heats an entire tank of water. And through the power of paying attention, I've observed that on a mild summer day after sunset, my air conditioner can only drop the temperature inside my home by about 1 degree Fahrenheit per hour. So, averaged across my whole home, using all 66 gallons of the hot water in the tank will only cool the house down by, at most, about 1.5 degrees Fahrenheit. Since the cooling effect this thing produces is mostly localized to this one room, I knew that in here the temperature drop would be greater than 1.5 degrees Fahrenheit, and it is. But because the furnace keeps kicking on periodically, what with the whole "it's winter" bit, that 6-degree temperature drop is about where it bottoms out, and when the water heater stops running, the room warms back up pretty quickly. Honestly, spring and fall, the times of year where I'm not using heating or cooling all that much, are when this thing becomes most noticeable. Unless my HVAC system kicks on, then the water heater really does chill just this room, and the effect can be more significant. Which is what all this other nonsense in here is for. Genuinely, all that work turned out to be mostly nonsense. There are still some things I want to tinker with, but it really is tinkering, and the kind that only a weird nerd like me would want to do. I hope at this point I've successfully convinced you that the cooling effect these create is just small potatoes. Those potatoes are so small, in fact, that if I ever wanted to use this room as an office or whatever, a space heater would be able to overcome the cooling of the water heater and keep it nice and warm. The logic of doing that is kinda questionable, but I'll get into that later. Now we should discuss the big potato. The thing that genuinely is a potential showstopper. How slow these things are. This is, indeed, the slowest water heater you'll ever live with. When I first installed it, because I didn't have the duct run to it yet and it kept re-ingesting its exhaust thanks to the shape of the closet, it took 13 hours of running non-stop to get the tank up to temperature. Once I got my ducting situation sorted, a new "what happens when you run out of hot water" test showed that it did improve somewhat to 11 hours, and that was after I had raised the set point to 130 degrees Fahrenheit out of preference. And now that we're in summer, because the incoming water temperature has warmed up and thus it has a head start, that time has improved again to 7 hours. But that's still a long time to wait to get your hot water back. The thing is, though, when it's charged up with 66 gallons of hot water, it takes a lot longer to burn through it all than you probably think it does. For instance, one of the first tests I did was to fill my bathtub with piping hot water, which draws about 30 gallons, or not quite half of the tank, and then I hopped in the shower after starting a stopwatch to see just how long it would take to run out of hot water. And folks, I was getting bored. It took more than 45 minutes of very hot showering to use the remaining 36 gallons of hot water. Now, obviously, different shower heads go through water faster than others, so my testing doesn't necessarily line up with your reality. But I've never thought my shower heads were all that water-saving, so assuming yours are similar, then I reckon you can probably get nearly 90 minutes of continuous shower time out of just one tank of hot water. The catch, of course, is that an ordinary water heater only takes an hour or two to recharge when it runs out, which is simply a minor inconvenience. If you run out of hot water from this thing in the winter, you might not get it back for 11 hours. But before you freak out about that, you should know that water heaters are a little peculiar. See, as is the case for all storage water heaters, the tank is filled via a dip tube which delivers cold water to the very bottom of the tank, while hot water is drawn off the top. This is done because hot water is less dense than cold water, so it floats, and a sharp boundary layer keeps the already hot and the incoming cold water separated, and they don't mix. This means that if you and a partner end up using, say, half the water in the tank for your morning showers, then you don't end up with a water heater filled with lukewarm water. Instead, you'll have 33 gallons of piping hot water floating on top of 33 gallons of cold water. This not only means you still have plenty of hot water ready to go for whatever you might need, but also the water heater only has to heat the 33 gallons you used. Therefore, the actual time required to recharge from those showers is just 5.5 hours. That's still quite a long time, of course, but if nobody's going to use hot water again until the evening, does that actually matter? I can't answer that for you, but no, it doesn't. Look, obviously some households use a lot more hot water than others do. Tankless water heaters wouldn't exist otherwise. So I'm not going to pretend that these are a good idea for literally everyone. But there are many, many hours in the day in which you are not using any hot water. For instance, when you're at work, or when you're at sleep. What actually matters is whether the water heater can recover hot water faster than your household uses it, which, if you've never run out of hot water before with a conventional storage water heater, either gas or electric, it almost certainly can, especially if you go up a size. But there is some nuance to be aware of. You might have seen an earlier video of mine where I talked about electric water heaters and how they have two heating elements, one at the bottom of the tank and another about halfway up. The one up top is there so that if you're in danger of running out of hot water, or genuinely run out, it can heat just the top half of the tank. With less water to heat, it heats up much faster, and you'll have at least some truly hot water available after 30 minutes or so. And then it will switch to the bottom element to heat up the rest. But these 120-volt plug-in heat pump models can't do that. They heat the entire volume of water as one. That presents both a hard limit and a rather inconvenient consequence for going over that limit. The 11 hours it takes to bring a full tank of ice-cold winter water up to 130 degrees Fahrenheit tells us two things. First, if you never use more than its entire tank capacity in a 12-hour period, you're never going to experience running out of hot water. It will always be fast enough to catch up to you. But it also tells us how fast the heat pump actually is. I mean, how slow it is. The heat pump can only raise the temperature of the entire volume by about 7 degrees Fahrenheit per hour. So if you cross that limit and use more than 66 gallons in an 11-hour period and end up running out of hot water, it could be a while before you get your hot water back. Now again, I must point out that typical usage patterns make running out of hot water very unlikely in the first place. Even if everyone in your household showers in the morning, by the time people are back from work and school, the water heater will probably be completely recovered, and everyone could shower again if they wanted to. But the bottom line is, if running out of hot water is anything close to a regular occurrence in your household, these plug-in models are just not going to work for you. Though, hot take, maybe that's a sign you're going a little heavy on the hot water there. Fun fact, you are in control of your own choices. Anyway, now let's get into some of the weird nerd stuff. But for those of you who don't care about that, my basic conclusion, which I hope I've convinced you of, is that these things are great. A large majority of households will be adequately served with one of these, and the trade-offs, though real, are pretty minor. And in the summer, some of them are not trade-offs at all. I don't regret this one bit. And if you don't care to learn more, bye, and thanks for watching. But I will tell you about the two minor issues I've encountered with this thing. The first one is incredibly strange, and I cannot explain it. 3, maybe 4 times now, not long into taking a shower, the water suddenly got cold for about 60 seconds. It wasn't ice cold, but like, you're running out of hot water cold. But then it got plenty hot again. I have no idea why or even how that happened. It doesn't seem possible for a small slug of cold water to end up near the top of the tank. But it has happened a few times with seemingly no rhyme or reason. My speculation is that since the tank is heated externally, weird convection currents might sometimes happen in there, which will occasionally produce that outcome. But I really don't know. Oh, and that leads me to one thing I'm really curious to discover. I think it's possible heat pump water heaters like this will have far fewer problems with mineral buildup over time. Since nothing inside this tank gets hot enough to produce bubbles of water vapor and nucleation sites, I wouldn't be surprised if far fewer minerals are able to precipitate out and build up. That might make these things last an unusually long time, though again, that's just speculation. It also appears A.O. Smith may be having some reliability issues with these. Yeah, I bought the extended warranty. And speaking of potential reliability issues, the other minor issue I had just happened a few weeks ago. This current leakage detection device on the power cord randomly tripped, and I didn't notice the water heater hadn't been running for a while. I think this probably happened when we had quite some gnarly storms roll through, which caused quite a lot of flickering of lights, though thankfully I never lost power. I'm guessing it tripped when the power was futzy. Luckily, I noticed it soon enough that I just reset it and it wasn't an actual issue for me, but it could have been. Oh right, I never explained the second reason I went with this model from A.O. Smith. Despite being a 120-volt plug-in model, their heat pump water heaters are, in fact, hybrid heat pump water heaters with resistive heating elements as well. This not only provides me with a backup should the heat pump fail, but if for whatever reason the heat-sucking part of this whole deal does become a problem, I can switch it to resistive mode and it will become an ordinary electric water heater. It even has those two heating elements and can do the same only heat the top half of the tank trick as all the rest. But those heating elements only put out 900 watts. So if you thought it was slow before, oh boy! In truth, it won't become all that much slower. The same 50 degree to 130 degree climb, which takes 11 hours with the heat pump, should take a little over 14 hours with 900 watts of heating power, assuming zero losses. But again, that's not necessarily a problem. In fact, I've been annoyed that nobody has made 120-volt resistive water heaters before. If your hot water usage is modest, do you have to care that it takes half the day to heat up the whole tank? I wouldn't, but nobody would sell me such a water heater until quite recently. But the only reason I ever envision wanting to switch it to resistive mode won't happen until the future. And even then, I probably still won't do it. So, remember me saying the logic of using a space heater in the same room as this thing was a bit questionable? That's because if you are heating the room with resistive heating, and the water heater absorbs that heat with its heat pump, well then you've pretty much defeated the point of using the heat pump. You've just created a slow, ordinary electric water heater with extra steps, so you might as well just switch it to resistive mode and have it stop sucking heat out of the room. But guess what? For me, in the winter, this is a slow, ordinary gas water heater with extra steps. All of the heat this thing was absorbing over the winter came from my gas furnace. Which is a bit ironic, since the major reason I wanted one of these is to reduce my use of gas. But it's only a bit ironic, because I am, in fact, reducing the use of gas quite substantially. For a start, my furnace only runs about half of the year. From late April to early October, I do not need to heat my home at all, and since my previous water heater made hot water with fire, and this one doesn't, it's a total elimination of gas during the warm months. But even during the cold months, I'm saving some gas. My furnace is more efficient at turning gas into heat than my water heater was. So even though it might feel a bit silly to do this two-step process, it is a slight savings, and I care about that. But before too long, I intend to replace the furnace with a cold climate heat pump, and that is why I wanted to get this hybrid model. Well, that needs picking apart. To reiterate, the point of heat pumps is that they can move more heat than it takes to run them. A good heat pump, like this water heater, will be able to move 4 times as much heat into my home than a resistive heater would release using the same amount of electrical energy. So, if my home is heated with a heat pump, and that heat ends up getting gobbled up by the water heater, it may seem a bit silly, but it's perfectly rational. It's just a very strange cascading heat pump setup. But for my home, I don't want to oversize the heat pump, and if it's sized correctly, then it will barely be able to keep my home warm in the coldest weather we experience. This water heater sucking some of that heat out of the air could potentially tip the scale just enough to become a noticeable problem. So, if that ever happens, switching it to resistive mode will make that problem go away while still providing hot water, just more expensively. So now I'll finish up by going over some cool heat pump facts revealed by having this plugged into a smart outlet this whole time, and finally I'll explain all this nonsense. When we are dealing with pure refrigerants, as is the case inside the refrigeration circuit, the pressure of that refrigerant tells you its literal temperature, and vice versa. And as temperature goes up, so does pressure. This means that as the water in the tank warms up, refrigerant pressure on the high side slowly climbs, which makes the compressor work harder and harder. And we can see this in the power draw, and in fact, the instantaneous power draw can give us an estimate for how close the water heater is to finished. Here's what the day it was installed looked like. When it was first plugged in, it actually didn't start the heat pump and instead used the resistive elements. It's programmed to do that when the average temperature in the tank is below 55 degrees, and being filled with ice-cold water on February 3rd, it definitely was. But after about an hour of that, it switched the heat pump on. And because the water was so cold, the refrigerant condensed into liquid at a very low pressure, probably like 60 psi given this is charged with R513A. This meant the compressor was barely doing any compressing, and power draw wasn't even 300 watts. But as the water got warmer and the pressure started climbing, the power draw slowly went up and up and up until hitting a max of roughly 460 watts. That's a pretty huge difference, but so is the pressure difference. At 120 degrees, R513A condenses at 180 psi, 3 times the pressure. But because the refrigerant needs to actually be hotter than the water to heat it, it was probably condensing around 135 degrees Fahrenheit, which would be a pressure of 220 psi. That's why it's working so much harder and drawing more power. When set to the factory default of 120 degrees Fahrenheit, it would essentially always stop at 460 watts of power draw. But when I bumped the set point up to 130 Fahrenheit, it would climb all the way to 500 watts. This is the highest temperature I would ever set it to for efficiency's sake. But what's interesting is every time you draw hot water out of the tank and some cold water enters at the bottom, refrigerant pressures immediately fall, and so power draw does too. Here I was doing laundry and set the washing machine to hot. Normally I don't do that because modern laundry detergents work great in cold water, but I wanted to see how much hot water laundry day might need. After starting the first load, the water heater did start up, but you can see right here that when I started the second load, the normally linear climb in power draw was interrupted. It basically went right back to where it started. And the same thing happened again when I started a third load. Now, as you can see, it only ran for 4 hours total, so it never got close to running out of hot water, and laundry day is a piece of cake. But I will acknowledge that I have a front-load washer which is very miserly on water usage, so the picture might not be so rosy with an old-school washer. But seriously, wash your clothes in cold water, it's fine. But the other interesting thing about the condensing temperature of the refrigerant is that we can look at the power draw to get a sense of the average water temperature inside the tank. For example, here power draw began around 400 watts, since it was just replenishing from me taking a shower, and most of the water in the tank was still very hot. But here I filled the bathtub, and since that draws nearly half the water from the tank, the average temperature was much lower, and so was the refrigerant temperature and thus the power draw. But you'll notice here it shut off early. It has done this on occasion with no apparent rhyme or reason, but usually it doesn't result in a noticeable change in water temperature since the water at the top of the tank is still close to where you want it to be. But I will say there have been some occasions where the water wasn't quite as hot as I was expecting. In fact, that's the main reason I ended up raising the temperature to 130 Fahrenheit, though I've always liked my water heaters on the hot side. And speaking of odd behavior, I also wanted to figure out whether this thing would end up fighting my humidifier. The humidistat video I made over the winter is actually what got all this started. See, this humidifier, like many, works much better when supplied with hot water, which is why it is. But since drawing hot water will eventually cause the water heater to switch on and start dehumidifying, well, a potential endless conflict appears. But luckily, it seems the designers of this thing were thinking ahead. This tank is really well insulated. That's part of why it's so huge. So if you don't use any hot water, heat leaks out so slowly that it only needs to switch on about every 13 to 14 hours. And while I don't know if they all work like this, with a full tank of hot water, it ignores small draws. Even if I take a 20-minute shower, it usually doesn't react to that. Unless you draw some minimum volume of water out of it in one go, which I'm estimating to be between 15 and 20 gallons, it will effectively just sit there and wait until the top portion of the tank has cooled off enough to justify starting back up. I'm guessing this was done by moving the bottom temperature sensor a good way up the tank, and that it was done specifically for humidifiers. My old water heater, and indeed every other I've ever paid attention to, would fire up almost immediately after you start using hot water. In fact, it would start up twice during the course of a dishwasher cycle, which probably uses 6 gallons tops. And so the old water heater would typically respond to the humidifier after it had been running for 15 minutes or so. But as far as I can tell, this water heater has never responded to the humidifier. It might run just a bit longer the next time it fires up, but it'll make it all day before that happens unless I use hot water in some other way. So I can happily report that all winter, there was never a problem. This room did get drier whenever it finally decided to start, but the rest of the house stayed delightfully moist. But speaking of the rest of the house, let's finish up with all this nonsense. It is true that my HVAC system's one and only air intake is in this room, but the shape of this room causes much of the air discharged by the water heater to be trapped. Virtually no airflow moves across the room, because the supply register which provides heating and cooling from the furnace is on the same side of it as the air intake, and thus it creates this massive dead zone. And the utility closet is in that dead zone. So when the water heater runs, pulls in air from over here and discharges it into the closet, once that cold air seeps out, the furnace isn't actually grabbing all that much of it. This means, especially in the spring, this room did start to get kinda chilly at times. And because I'm me, I solved that problem with a bathroom fan, a temperature controller, and a second thermostat. So that bathroom fan mounted to the wall pulls air from the back corner of the closet, which is right near the water heater's exhaust vent, and blows it through this duct to push it out of the closet right above my furnace's air intake. I even used one of those outdoor vent covers to make sure it's throwing air down and right where the furnace will gobble it up. That fan will come on when the temperature controller it's plugged into detects the temperature in this closet has fallen below 57 degrees. And this analog thermostat up here is wired across the R and G terminals of my furnace to make the furnace fan come on at the same time. Now, regardless of whether my thermostat is requesting heating or cooling, when the water heater starts running, the furnace fan and the bathroom fan will help move the cold air from inside the closet, get the furnace to suck it up, and spread it around my home. Now, this works, and it works decently well. But it's also extremely kludgy and weird. I only did it like this because this closet is so cramped. It seemed kind of fiddly to run another 6-inch duct to the water heater, especially since it has to get behind the water pipes to connect to the exhaust collar. And because I can think of a whole bunch of other situations where a blower fan could be the ideal solution to give these things air, I would like to see heat pump water heaters equipped with an auxiliary power outlet which is energized whenever the compressor is running. This temperature controller solution works, but not all that well. In fact, it's not working much at all in the warmer weather because it usually doesn't get colder than 57 degrees in the closet, and I need to adjust the set point. So I'd rather just have some way to turn on the fan whenever the water heater is on, which an auxiliary power outlet would let me do. I'd also like to see an auxiliary relay so you can send a fan call to an HVAC system at the same time without hooking up a second thermostat. But you know, I've got stuff and I know how to use it. But I was caught off guard by how loud that bathroom fan would be. And it's not actually because of the fan. I deliberately got a very quiet one. It's mostly because of this vent. Since this awful bathroom fan situation ended up making more noise than I expected, and since actually getting it to work well would require fiddling with the set point throughout the year, I am going to try and run another 6-inch duct to the water heater's exhaust collar and put a larger and more normal kind of vent where this one is. After doing that, in theory, I can remove the intake duct and put that vent back to code-compliant status. Once I do this, the water heater itself will solve the dead zone problem in this room, and since its discharge air will still be right above the furnace intake, distribution throughout my home should be the same as now. I am mildly worried that an exhaust duct might sweat with condensation in the warmer and more humid parts of the year, but this room does get pretty dry after it's been running for a while, and it always runs for at least 2 hours at a time, so I'm not sure whether that will actually be an issue. I'll pin a comment if it does. And well, I'll also have to play around with new solutions for forcing the furnace fan to come on. I'm thinking what I'll probably do is just move that thermostat outside the closet and right next to the discharge vent. It's a dumb solution, but I tend to prefer those, and it'll make adjusting the temperature at which the furnace fan kicks on throughout the year trivial, while also giving me the option to disable that outright. And that's about it. But I do have a loose end to tie up. That video I mentioned on electric water heaters, at the end of that one, I told you about a mystery box I threw together which would allow me to disable the water heater when electricity prices are high. I'm on variable electricity rates because I'm a sicko who likes to game that sort of thing. All that box was a 40 amp contactor with a 120 volt coil wired to a plug, which I plugged into a smart outlet so I could limit when the water heater got power to the overnight hours, when electricity is very cheap. Doing this had absolutely no noticeable effect on hot water availability, since I never used the entire tank in a day, but it also didn't really have an effect on my power bill. In truth, it probably had some, but the impact was far too small to pick out from everything else I use electricity for. Also, back then, I wasn't living there full time. It's a long story, but my already pretty low hot water demand was magnified by that fact, and so I was saving very little money by shifting the energy draw to the overnight hours. This modern heat pump water heater has Wi-Fi and Bluetooth, because of course it does, and can thus participate in demand response programs if that's your jam. But because it's such a small power draw, I'm honestly not interested in trying to optimize when it runs. Besides, if your family's big enough to push this to its limits, it'll be running most of the time anyway, so there's not much savings to have. But anyway, okay, this is the end for real now.
Hey, so remember how I had all those other data loggers running? Well, that means I have a lot of data sets that I didn't show you here, mostly because it was all pretty minor stuff and not really relevant to the grand scheme, but I was logging stuff such as what is the actual air temperature inside my ductwork while the furnace fan has kicked on in response to the water heater running. So if you're interested in a more in-depth discussion about this, as well as a story about how Lowe's managed to lose this water heater for like 2 weeks, well, you can check out the video on Connextras, which will be popping up at the end screen.
Oh, well, I just did this backwards. Why did I change that line? I don't know. None of it...